Hi everyone, in this video we're going to investigate the system that I've sketched out here, in which we have a particle sliding on a smooth wedge, which itself is sliding along a smooth horizontal surface, and the particle has mass lowercase m, the wedge has mass capital M, and the opening angle of the wedge is theta. So of course, if you want to describe the time evolution of a system, you need to define some sensible generalized coordinates for that system. So the two coordinates that I've defined here are capital X, which is the horizontal displacement of the lower left corner of the wedge relative to some fixed reference position on the horizontal surface, and then Q, which is the distance from that lower left corner to the particle along a line of greatest slope of the wedge. There are, of course, many other ways that you could parameterize this system, but to me this felt like the most natural thing to do. So we also need initial conditions, and the initial conditions that we're going to impose here are that X and X dot at time 0 are both 0. In other words, the wedge itself starts at the reference position and starts stationary, but we are allowing Q of 0 to be some positive value L and Q dot of 0 to be some arbitrary value U. In other words, we're starting the particle wherever we want along the slope of the wedge, and we're giving it an initial velocity either up or down the wedge depending on whether U is positive or negative. I also want to mention now that after we've found X of t and Q of t, we're not just going to stop there, but we're going to try and interpret our solutions by considering some interesting limiting cases and making sure that they make physical sense. So there are various different approaches you could take to this. I'm going to do it using Lagrangian mechanics because I think that's kind of fun. It can be done just using Newton's second law if you think carefully about it, but let's take the Lagrangian approach, which means the first thing we need to do is write down expressions for the potential energy and kinetic energy of the system in terms of the generalized coordinates. Let's do the potential energy V first because that's comparatively straightforward. Now in this system, the potential energy is purely gravitational. The gravitational potential energy of the particle is going to be lowercase m times g times the vertical displacement of the particle above our reference height. Now we're going to take our reference height to be the horizontal surface, and so if you just project your generalized coordinate q in the vertical direction, you can see that that height is going to be q sine theta. Now there's also some gravitational potential energy due to the fact that the center of mass of the wedge is not at 0 height, right? It's not at the location of the horizontal surface. However, because the wedge is not moving up and down, the gravitational potential energy of the wedge is just a constant. So what I'm going to do is put in brackets here plus some constant, because we don't really care what the value of that constant is, because when we come to get our equations of motion, we're going to be differentiating our energies and constant terms are going to disappear. Right, now let's do the kinetic energy term T. The kinetic energy of the wedge is straightforward because it's just a half times capital M times the velocity of the wedge squared. The wedge is just moving left and right, and so its velocity is x dot. So we get half capital M x dot squared. Now, in order to deal with the kinetic energy of the particle, it's actually best to think in Cartesian coordinates temporarily. So let's say that the particle has Cartesian coordinates x and y. The origin of that Cartesian coordinate system doesn't really matter, but it's most straightforward to think of if you place the origin right here at this cross. In other words, you place it at the position from which we measured our generalized coordinate capital X. So let's express lowercase x and y, the Cartesian coordinates of the particle, in terms of our actual generalized coordinates capital X and Q. So as a column vector, xy is going to be equal to, well, the x coordinate of the particle has two contributions, because as the wedge moves left and right, the particle sort of automatically moves left and right because it's on, the particle is on the surface of the wedge. So there is a factor of x, but then we have to add on the horizontal sort of component of the displacement in the q direction, which just involves a bit of resolving, and resolving horizontally gives q cos theta. So it's capital X plus q cos theta. The y coordinate is even easier, and in fact we've already done the y coordinate without explicitly saying it when we wrote down our potential energy. It's just q sine theta because we are resolving in the vertical direction. Then to turn those into velocities, which is what we need for kinetic energy, all we need to do is differentiate everything with respect to time. So we put dots on the coordinates, and then we just put dots on our x's and our q's, and theta is a constant, so we don't need to worry about that. Now the point of this is that we can nicely express the kinetic energy of the particle in terms of its Cartesian coordinates. It's just half times lowercase m times the velocity squared, which would just be x dot squared plus y dot squared, right? That's just particularly easy in Cartesian coordinates, but we now have expressions for x dot and y dot in terms of our generalized coordinates, so we can express t in terms of capital X and Q. So putting this all together gives the following. You've still got your half big M x dot squared. You've still got your half lowercase m, and then here's where things get interesting. So our x dot squared term is going to be this thing that I've just circled, all squared. So if you square that, you're going to get x dot squared, and you're going to get the other term squared, which is q dot squared cos squared theta, and then you're going to get your twice the product cross term, which is going to be 2 x dot q dot cos theta. And then we move on to the y dot squared term, which is just this thing squared. That's straightforward because there's just one term, and so it is just q dot squared sine squared theta. Now we can simplify this a bit. Most of the expression stays unchanged, but we can do something very nice with this term and this term, because sine squared theta plus cos squared theta is just 1, and so if you factor out a q dot squared, you've got q dot squared into sine squared theta plus cos squared theta, which is just q dot squared times 1. And so that bracketed term in simplified form becomes x dot squared plus just q dot squared, and then the cross term 2 x dot q dot cos theta. Then all we have to do is subtract the potential energy from the kinetic energy, as I've done right here. And that's literally just taking this and subtracting that, and you get your Lagrangian from which all of the dynamics of the system follow. So there's the Lagrangian up at the top. As always, now we just have to construct the Euler-Lagrange equations, and then we'll know how the system evolves with time. So we'll do the Euler-Lagrange equation for x first. So that says d by dt of dl by dx dot is equal to dl by dx. So for the time being, I'm just going to keep the time derivative written in there explicitly at the front. So d by dt of, then we differentiate L partially with respect to x dot. So if we deal with that term first, we just pull down a factor of 2, which cancels with the half and just gives you m x dot, capital M x dot, right? Then I'm going to keep my pre-factor of half lowercase m so that I can differentiate the bracketed stuff term by term. The x dot squared just becomes 2x dot. The q dot squared doesn't depend on x dot, so that disappears. And the cross term depends linearly on x dot, so you just get the coefficient of x dot, which is 2q dot cos theta, close brackets. And the potential energy bit doesn't depend on x dot at all, and so that doesn't contribute anything, so I just close my brackets there. The right-hand side of this Euler-Lagrange equation is dl by dx, but there is no explicit x dependence at all in the Lagrangian, and so that partial derivative is just 0. So now what happens? Well, this half cancels with this 2 and this 2, and then we do the time derivative, which just adds a second dot to each of the existing time derivatives, right? And so the resulting equation of motion can be written as m plus m x double dot plus small m q double dot cos theta is equal to 0. Now, before we move on, does this equation have a nice interpretation? Well, as it turns out, it does. If you consider the physical meaning of the stuff inside the square brackets at the stage where I still had left the time derivative explicitly at the front. So that's because this first bit, capital M times x dot, is just the linear momentum of the wedge in the horizontal direction. Then the remaining terms, you've got lowercase m times x dot plus lowercase m times q dot cos theta. Now the sum of those two terms is the linear momentum of the particle in the x direction. That last term there is necessary because you would have to resolve your q velocity q dot into the horizontal direction, hence the cos theta. And so the interpretation of this equation is it's just saying that the time derivative of the total momentum in the horizontal direction of the system is just 0. In other words, horizontal momentum is conserved. This is ultimately an example of Noether's theorem, if you're familiar with that theorem, which basically says that if the Lagrangian doesn't depend on a particular generalized coordinate, then there is some associated quantity which is conserved. And here the Lagrangian doesn't depend explicitly on the x-coordinate, and hence the momentum in the x direction is conserved. So now we have to construct our other Euler-Lagrange equation. which just involves differentiating with respect to q dot and q instead of x dot and x. So once again, let's keep the d by dt explicitly in the front at first. This term doesn't depend on q dot, so that disappears. Then you've got your half m prefactor again. Right, again, x dot doesn't depend on q dot. Q dot squared becomes 2q dot. The cross term depends linearly on q dot, so you get the coefficient of q dot, which is plus 2x dot cos theta. Close brackets, again, this part doesn't depend on q dot, so we close our time derivative. The right-hand side in this equation is not going to be 0 because dl by dq isn't 0 because there is this explicit q dependence in the Lagrangian. So that term, the potential energy bit, is just linear in q, and so we differentiate with respect to q, and you get minus mg sine theta. So once again, you cancel the half and the 2's, and you put an extra dot on each of the time derivatives. And we can also, in this case, actually cancel m from both sides, right? You've just got a lowercase m here and here. And so your equation of motion is going to be q double dot plus x double dot cos theta is equal to minus g sine theta. Now, does this equation have a nice interpretation? It sort of does if you consider Newton's second law to be a nice thing, because you could have actually got this equation from applying Newton's second law. So if we just, let's actually stick the m's back in for a second. So then it looks a little bit like F equals ma. This would be your ma term in the q direction, right? So sort of resolving forces parallel to the slope of the wedge. So the right-hand side is easy to interpret because that's just the weight of the particle projected in the direction parallel to the slope of the plane, and it has a minus sign because it's acting down the plane. Then this middle term is basically a fictitious force that arises because we are in an accelerating frame, right? We are measuring the coordinate q of the particle relative to the wedge, but the wedge itself is accelerating, and so if you want to apply Newton's second law, you have to insert an appropriate fictitious force to take account of that acceleration. So it all comes very naturally out of the Lagrangian formalism, but the point there is that you could have got it just by applying Newton's second law, as long as you were sort of careful enough to include the appropriate fictitious force term. So just to summarize the results of what we've got so far, we have equation 1, I'm going to call it, this one here, and equation 2, which are both linear second-order differential equations for x and q that we're trying to solve. And so we can just solve these as a pair of simultaneous equations, and I'm going to do that by rearranging the second one for q double dot and substituting that back into the first one. So let's write out the equation that we get from that substitution. You've still got your m plus m x double dot as the beginning term. Then we're going to replace this q double dot with stuff from the second equation, right? So we're going to have m cos theta multiplied by q double dot, but according to the second equation, q double dot is the same as minus g sine theta minus x double dot cos theta, and all of that is supposed to be 0. So what you can do is just rearrange this to make x double dot the subject. So if we just collect together all of the x double dot terms, what's the overall coefficient of x double dot going to be? Well, you've explicitly got big M plus small m written in there. That's very easy. But you've also got this x double dot term. When you expand those brackets, you're going to get minus little m cos squared theta times x double dot. And so if you group that together with the existing m plus m term at the beginning, you're going to have an additional minus small m cos squared theta in those brackets. So then you're just going to move the m cos theta times minus g sine theta to the other side, make it positive, divide by the prefactor, and putting that all together, you will find that x double dot is equal to mg sine theta cos theta divided by m plus small m sine squared theta, where I've just used the fact that 1 minus cos squared theta is sine squared theta to combine those two circle terms into one term. I've just had to clear some space, but I've kept the key information, which is the two equations of motion that we're trying to solve, and our result for x double dot that we just derived. Now, the important thing about this is it implies that x double dot is just a constant because there is no dependence on time in that fraction on the right hand side. So all we have to do is integrate it twice, and then we'll know x as a function of time. So integrate it once and you get rid of one of the dots. So x dot is going to be equal to, well, let me copy and paste this whole thing because it's just going to be that multiplied by time plus some arbitrary constant in general, which I'm going to call alpha. And then, of course, we just integrate one more time to remove the remaining time derivative. And so we're going to get that same factor. But now when we integrate this t, you're going to get a half of t squared. So let's just put t squared over 2. You integrate alpha, you get alpha t, and then you get your second constant of integration, which of course I'm going to call beta. And so this is the totally general solution for x as a function of time. Now we just need to apply the initial conditions that I specified. The initial conditions for x were simply that x of 0 and x dot of 0 are both equal to 0. So if x dot of 0 is equal to 0, then from our expression for x dot over here, that implies that alpha needs to be 0. And then if x of 0 is also 0, that implies from this equation here that beta needs to be 0. So everything works out very nicely because the arbitrary constants are just 0. So all I have to do is copy this bit, right? Ignore those constants because they're 0. And we have solved for our specific time evolution of x. Great, so what about q? Let's solve for q, and we're going to solve a very similar second order differential equation for q, but we first need to derive what q double dot actually is. You can do that using equation 2 up at the top here, because you can very straightforwardly rearrange it for q double dot. It's minus x double dot cos theta minus g sine theta. We know already that x double dot is this. So I'm going to start by copying that and putting it there. When we move this term to the other side, of course, it's going to acquire a minus sign. So I better stick a minus sign in the front there. And then it also has an extra factor of cos theta. And so this cos theta is going to become cos squared theta, right? Then what we'd need to do is subtract from that g sine theta. But of course, I'm dealing with fractions, so I need to put that over a denominator of big M plus small m sine squared theta, which means I need to multiply by the same thing on the top. So big M plus small m sine squared theta on the top. Now this is much easier to simplify than it might look, because you've got, if you look at your numerator of your first fraction, you've got mg sine theta times cos squared theta. But then one of the terms in the second fraction is mg sine theta times sine squared theta. So we can again make use of that identity that cos squared plus sine squared is equal to 1, and just combine those into a single term, right? And so q double dot simplifies very nicely to just minus big M plus small m from combining your cos squared and sine squared times g sine theta over, well, the same denominator. Then just like we did with x, we're going to integrate it twice. I'm going to do it in one step this time because I think you get the idea. We're going to get two constants of integration. So I'm going to write it this time as gamma plus delta t minus, and then let's just copy this. And that is going to acquire a time dependence of t squared over 2. So gamma and delta are your second two arbitrary constants. So now all that remains to be done is to fix the values of the constants gamma and delta using the initial conditions. So if we first apply the fact that q dot at time 0 is equal to u, well, if you differentiate this, this term is going to become linear in t, this term is going to disappear, and you're just going to be left with delta. And so the implication is that delta has to be equal to u. What about your other initial condition? Well, that was just that q of 0 is some arbitrary positive value, L. So when you substitute t equals 0, this term and this term both disappear. And so the implication is that gamma has to be L. So gamma is equal to L. And so to write my general, sorry, not my general, my specific solution for q, all I have to do is copy this out and replace gamma with L and replace delta with U, like that. Now, as I mentioned at the beginning, our goal here is not just to get some equations and then forget about them, but try to develop some intuition about them. And a very good way of gaining intuition about equations is to consider limiting cases. So I've got 4 specific limiting cases that I want to consider, just to make sure that these solutions make physical sense. And we'll do the easiest one first, which is just what happens when theta is equal to 0. Well, when theta is 0, this sine theta factor forces x to always be 0 for all time, right? So x is just identically equal to 0. And this sine theta term in q forces the quadratic term to disappear and means that q is just equal to L plus ut. So what's the physical meaning of this? Well, when theta is 0, you basically don't have a wedge at all, right? There is no slope, and so it makes perfect sense that the x-coordinate of the slope remains 0 at all time, because the particle is just pushing straight down on a flat surface, and there would be no reason for the wedge to actually move left or right. What about how q evolves with time? Well, this is just saying that the distance between q and its starting point, which was at a value of L, just increases linearly with time, and that's perfectly consistent with a particle that initially has a speed of u but doesn't have any force acting on it, right? It's just going to keep going in the same direction forever with a speed of u. So that's great. What about when theta is another special value, which is pi over 2? Well, when theta is pi over 2, cos of pi over 2 is 0, so the cos theta term, again, forces x to be identically 0 for all time. What about the q term, though? The last term is not going to disappear because you've got sine theta instead of cos theta. So you've got q is L plus ut plus something. Now, sine of pi over 2 is 1. So you can imagine that basically that disappears and that disappears. And so it's m plus m times g over m plus m. So the m plus m's would cancel in this case, and you'll just get minus a half gt squared. So let's put minus a half gt squared. What's the physical significance of that case? Well, if theta is pi over 2, then, well, there's a right angle. Like, the wedge is a right angle, and so it's not really sloped, it's just vertical. So if it's not sloped, then the weight of the particle is not actually pushing the wedge at all, right? There is no contact force between the particle and the wedge. The particle is just going straight down, and the wedge doesn't have any horizontal force acting on it. So again, it makes sense that in that case, the wedge wouldn't move. And this equation here is exactly what you would get for a particle in free fall moving vertically. And q is just equivalent to a y coordinate there, right? It's a vertical coordinate. Exactly what you'd get from SUVAT with an acceleration of just g, of course. So now we're going to make our limiting cases a little bit more complicated, and we're going to allow theta to be whatever value it wants to be, and consider what happens when the mass of the wedge is much bigger than the mass of the particle. So for x, look at the denominator here. The big M term is going to dominate if that's much bigger, while the numerator is tiny, and so x is going to be not 0, but a very, very small value. And so we could say that x is approximately 0. That's not very quantitative, but for sort of intuitive understanding, we can just think, okay, x is a value that's so small that it's basically just 0. Okay, so again, it's not moving. What about the particle? What happens to q? Well, as always, you've got your L plus ut. If big M is much bigger, then this term basically disappears, right? Because the big M term dominates. And this plus little m also disappears. So you've got minus a half g sine theta t squared, because the big M on the top would pretty much cancel with the big M on the bottom. So let me just write that out. It's minus a half g sine theta times t squared. So the interpretation here is if the mass of the wedge is huge, then it has lots and lots of inertia, so it doesn't really want to move. So it makes sense that its x-coordinate remains very, very close to 0. What about this equation? Well, this is, again, exactly what you would get from SUVAT, but this time the acceleration is not g, it's g sine theta, because what's happening is the particle is sliding down a wedge which is still sloped. So the g sine theta is the gravitational acceleration projected down well, projected in the direction which is parallel to the slope. So finally, the most mathematically complicated special case I want to consider is what happens when small m is much bigger than big M. So it might be interesting for you to actually pause the video here for a few moments and consider what you expect to happen just intuitively. And then we'll work through the equations and see if your predictions are consistent with what the maths tells us. So let's see what actually happens. If small m is much bigger than big M, then for x, this capital M is basically negligible on the denominator. So let's cross that off. And then the small m on the top and the bottom are going to pretty much cancel. Then you've got sine theta cos theta over sine squared theta. One factor of sine theta cancels, and then you've got cos over sine, which is cot. And so we can say that x is roughly equal to half g cot theta times t squared. Now, as always, q starts off with those same terms, L plus ut. Which terms are going to be negligible in the fraction this time? We'll pretend the capital M isn't there. This capital M isn't there. Again, the small m's are going to cancel, but this time you've got sine theta on the top, sine squared theta on the bottom, so 1 over sine theta overall, or cosec theta, and so it's going to be L plus ut minus half g cosec theta t squared. Now, it's not particularly straightforward to just look at these and understand what's going on. What is useful to do is convert back to Cartesian coordinates of the particle, and that will give us some insight as to what's happening here. So remember that the Cartesian x coordinate of the particle, lowercase x, as we discussed at the beginning, is capital X plus q cos theta. Let's deal with the q cos theta term first, because you get some easy terms from this L plus ut bit, right? So that is going to be, you get L cos theta, and you get plus u cos theta times t. Then with this last term, the cosec term, when you multiply that by cos, you've got cos theta cosec theta, which is the same as cos theta over sine theta, which is the same as cot theta, right? So you've got minus a half g cot theta t squared plus a half g cot theta t squared when you add your capital X, and those will cancel perfectly, and you've just got this simple linear function of time. Okay, well, that's nice. How about the y coordinate? Well, the y coordinate is just q sine theta. So you're going to get L sine theta. You're going to get u sine theta t, and when you do sine theta times cosec theta, that's just sine theta over sine theta, and so the trig bits cancel and you just get half gt squared. Now focus your attention in particular on the time dependent part, so this and this, because the L cos theta and L sine theta are just sort of the starting coordinates of the particle. So x is increasing linearly with a velocity or component of velocity of u cos theta, which is exactly what a projectile would be doing, right? And y, the y equation, is perfectly consistent with the Suvat equation in the y direction for a projectile, and you've got u sine theta because you've resolved your initial velocity u in the vertical direction, and it's just accelerating downwards always with an acceleration of g. So actually what's happening here is the particle is just behaving exactly like a projectile moving freely under gravity, as if the wedge were not even there. Now this makes sense because in this case the particle is the object that has lots and lots of inertia, and so it can basically just push the wedge out of its way. The wedge has very little inertia, it just moves to the right in exactly the perfect way to allow the particle to perform its projectile motion. So personally, I found that really interesting and satisfying because the equations look pretty complicated, but then you just recover these projectile equations at the very end, and it all makes perfect sense physically. Well, I think that's enough for this time. Thank you for joining me, and I'll be back soon with some more physics videos.